For the fourth notebook and fourth exercise of this Baltic waves practical session, we will mix the different datasets that we have used in the previous notebooks. So the wave model data and the physical model data. And we will extract the information of these different models at specific geographical location across a section in the Baltic Sea and also at a fixed point. So we're still using the same wave products, Hawley hindcast products, and the same physical model products, daily mean products, over the period of the storm event in January 2017. So again, we will use exactly the same functions to handle the data and to plot the data. So we first load the Python libraries. Then we define a folder to store the plots that will be generated during this training. And finally, we load the data. So first the wave data and then the physical model data. We will use again the open MF dataset function from the X-array library to open all the Hawley data from the wave model from the 9th of January to the 14th of January. All these files are stored in the data folder here and here. So you see here the 6 files for the wave data. So we define the route path and the file names, and we will load all the files that have this kind of file names here all together at the same time. We define the var name for the significant wave height and for the wave direction variable. We load the data and we store the information in specific variables, and then we print the significant wave height variable, and that's it. So you see here that we have now in this significant wave height array, we have 144 time frames, which correspond to the 6 files of 24 time frames. And we still have the same longitude and latitude grid, so that's as expected. Then we do the same for the temperature, the salinity, and the ocean mix layer data, using the daily data, again from the 9th of January to the 14th of January. So here we define the specific route path of this NEMO model data, and again the name of the files, and we load all these variables and all the dataset with the open MF dataset function. And we store the variables of interest in the var temp, parcel, and var ocean mix layer. And we print the var temp variable. And we also store the time, longitude, latitude, and depth in specific variables. And you can see here that the temperature variable has 6 time frames, and the number of the 56 depth levels, and the latitude and the longitude points as expected. So of course we do that separately for the two models, because they have different variables inside and different coordinates, and not exactly the same grid, so it would not be possible to load all the data at once from all the from the two different models, of course. So now we extract the data along the section across the Baltic Sea at a fixed longitude. So we are going to look at the data in depth along this section here. So we fix the longitude here. Of course, you can change this value and test different sections at different longitudes. And we find with a cell function the index in the different variable, the temperature, the salinity, and the ocean mix layer for the moment. We find the index of longitude that corresponds to the closest longitude to the fixed longitude, using the nearest method here. And so we have a reduced dataset along this line here. So do the selection, and you can see that now we have for this temperature variable, we still have the 6 time frames, we still have the 56 depth levels, we still have all the latitude points, but we don't have the longitude dimension anymore because we have fixed it to one value. You can see here in the coordinates it's only one value now, which is the closest one to the value we fixed here. So it worked well. And now we can plot the temperature or the salinity along the section at this fixed longitude. So we are going to set the parameters for the plots for the temperature, and if you want to do the same kind of plots for the salinity, you will have to validate this cell and not this one. You can see for both of these cells, you define the min and max depths for which we want to plot the profiles, the vertical profiles, the latitude extension. So here I plot all the basin, but here, for example, it's reduced to the Bosnian Sea only, but you can change that if you want to do some tests later on. Here we define the min and max temperature values for the color bar, and here you have the equivalent for the salinity, and here we say var, so the variable that we will plot is the temperature along the section, whereas here we say that it's the salinity. So of course we will only validate one of these two cells, otherwise we will replace the values in var by these ones if you validate both cells. So I validate the temperature one, and then I proceed to the plots. So for this plot, we will have one plot per time frame, and we will plot the temperature, in this case, as a function of the latitude and as the depth. So we will have a vertical profile of the temperature as a function of the latitude, and we will superimpose the ocean mix layer depth. So let's go. So you see here the different plots, one per time frame, of the temperature as a function of the latitude along the cross-section we have defined, and as a function of the depth. And here the black line shows the ocean mix layer depth. So what we observe is that during or when the storm event occurs, we see that there is an homogenization of the temperature in the first 50 meters of depth. Here, when you compare here, you see that you have this patterns here that have disappeared on the 11th and on the 12th. So there is a clear homogenization of the temperature in the 51st meters, which corresponds, of course, with the thickening of the ocean mixed layer here, as you can see along the time. We see the same phenomena here in this part, which is the Baltic Sea, where you can see that the temperature had showed some patterns here that are homogenized during the storm event. And then, after the storm has passed, we see again some relaxing in the temperature patterns, and the ocean mixed layer is becoming thinner again. So, of course, you can do the same kind of plots for the salinity, as I mentioned before, and you will see also some patterns occur. And you can also reduce the latitude section, for example, you want to plot, or you can change the color bar by changing the parameters in this cell. Okay, so clearly, when we looked at the maps at the surface in the previous notebooks, we could not see any clear difference from one day to the other. But when we look at deeper levels, we can see that there is clearly an impact of the storm on this on the temperature at this level. So you can go back to, if you want, you can go back to the previous notebook and try to plot the maps again at different depths, and especially close to minus 50 meters. And you will see some changes in your maps from day to day during the storm events. So, what do we, and yes, last point, if you want to do a section with a fixed latitude here, so in this way rather than this way, you can just change here the selection on the data by replacing the longitude by the latitude and defining a latitude fixed latitude here, and you will have new selection of data and you will do the same kind of plots. Of course, you have to change also in the plotting section that you want to plot as a function of the longitude and not as a function of the latitude. But of course, this is adaptable, and you can do the same kind of diagnosis with the fixed latitude. Okay, so now we are going to look at a fixed point in the Baltic Sea. So we fix not only the longitude but also the latitude at this point here. So we define our point. Of course, you can change it if you want to do other tests. And we find the closest longitude and latitude points in the model grid to this fixed latitude and longitude. And we do it for the waves parameters and also for the temperature, the salinity, and the ocean mixed layer. And you can note that the coordinates have different names in the two different models. So for the wave models, the longitude and latitude are called long and lat, while they are called longitude and latitude in the physical model. So I validate the cell, and you can see here some information about so the significant wave height variable extracted at the point of interest. So we now have only one dimension, which is the time, because we fixed both the latitude and the longitude. So you see here we just have one value for each of them. The same for the wave directions, and also for the temperature we still have 6 time frames and 56 level of depth, and again we fixed the latitude and the longitude. Then we are computing the eastward and northward components from the waves directions, as we did in the second notebook. And then we can plot the data. So here we define all the parameters to plot the data, the range of depth we want to plot, the minimum and maximum values for the temperature, the salinity, the significant wave height, and also we will only plot 1 time frame out of 4 for the waves data, because I recall that we have hourly data for the waves and daily mean data for the physical parameters. So we just have 6 days or 6 time frames for this physical model, while we have 144 time frames for the waves. So we reduced a bit the number just to have clear plots. And we will plot the information, we will plot the evolution of the physical parameters as a function of time and depth. So it's a kind of Hofmüller diagram. We will have the vertical profiles, but given as a function of time at the point we are looking at. And we will superimpose the ocean mixed layer position over the same period, so it's evolution over the time. And we will also plot on a separate or secondary axis the significant wave height during the same period and the wave direction arrows also over the time. And to plot these arrows, we will use the quiver function that we already used in the second notebook. So we plot we create a figure which will have 2 different subplots, one for the temperature and one for the salinity. And for the temperature, you see here that we plot, so with the p-color mesh function again, we plot the temperature as a function of the time and the depth. Then we add the ocean mixed layer depth as a black line as a function of the time. And on the secondary axis, we plot the significant wave height as a function of the time again, here, as you can see. And as I mentioned before, we only plot 1 time frame out of 4 using the time step W for wave variable here. And we also plot the wave directions here with a quiver function. And again, we plot only 1 point out of 4, 1 time frame out of 4. And we do exactly the same for the salinity. So let's validate. And here is the plot we obtain. So what do we see? I go back to my map here. So you see we are in the proper Baltic, in the Baltic proper basin here, where we have a large increase of the ocean mixed large thickening of the ocean mixed layer during the storm event. We have a thickening. And what do we observe? So in red we have the significant wave height as a function of the time, and given on the secondary axis here. And here we have the arrows of the wave directions. And for the same period, we have in color the temperature as a function of the depth and as a function of the time. So we see the evolution of the temperature along the time here. And here in black, we have the evolution of the ocean mixed layer depth over the time as well. So what we see is that during the storm event here, which is clearly visible in the significant wave height, with very large wave heights up to more than 7 meters, we observe this thickening in the ocean mixed layer depth, and we also observe this homogenization of the temperature along the water column. Up to minus 50 meter depth, as you can see here. And for the salinity also, it's less visible, but we have the same kind of phenomenon where you see that the salinity is homogenizing a bit along the water column up to minus 50 meters again depth during the storm event. And this corresponds, of course, to this drop to this thickening in the ocean mixed layer depth. So that's it. Of course, you can do another extraction of the data by changing very simply the longitude and latitude of the points here, and you can redo all these cells here and revalidate all these cells to plot new diagrams at other or at different points, and you will see the different behavior of the water masses in the basins during this storm event. So that's it, and I hope you enjoyed this training, and don't hesitate to contact us on the forum if you have any questions. Thank you for attention.